Hi everyone, welcome to my new class. So in today's class, I will be discussing the support reaction. This is a topic from engineering mechanics. It's equally important for mechanics of solids also. So mechanics of solids is considered to be the second or the continuation of engineering mechanics. So we have to study the support reaction thoroughly in engineering mechanics. That will help you to do problems in mechanics of solids. So here is the content I am going to do in this lecture. First, I will be giving an introduction what is support reaction, and after that we will go for types of loading, and in that I will be discussing point load, uniformly distributed load, uniformly varying load, and next we will be discussing different types of beams and its reaction, and we will be mainly dealing with the analytical method. There is a graphical method also for solving this kind of problem. That won't be asking for the university examination. So it will be, as an exam point of view, I will be discussing only analytical method. So what is the reaction force? According to Newton's law, when we apply any force on a system, the system will try to offer the equal and opposite force. Suppose we have some weight and we will be standing on the floor. So I am applying, suppose my weight is 70 kilograms. So I am applying 70 kilograms on the floor. I am not going down because the floor is offering same amount of force on me. That's why I am standing on the floor. If the floor is applying excess amount of force, I will be going in an upward direction. And if I am applying excess amount of force than the floor, I will be going downwards. So that is called a reaction. For every action, there is an equal and opposite reaction. For a system is in equilibrium. There is another example. Suppose there is a bridge made up of paper, and I am trying to walking through that bridge. What will happen? Obviously the bridge will break and I will fall down because I am applying again same amount of force I am applying, but the bridge is not capable of applying 70 kilogram reaction force. So that's why I will be going down. So the system is not in equilibrium. Here they have mentioned the case of a fan. A fan is hanging on their hook. The weight of the fan will be acting downwards, and the reaction of the rudder or hook will be acting in the upward direction, for the system is in equilibrium. So in this chapter we will be analyzing such kind of force acting on a system, and we will be finding out the reaction offered by the force. So we will be provided with the different types of force acting on a system, and the system may be bolted or hooked to some point. We will be finding out the reaction at that point. Okay. So next topic we will be discussing the types of load. The first thing we will be discussing the point load. So normally we will be representing the force as a arrow mark. So that means the force is acting if this is surface is 5 meters long and the force is acting this point. So this kind of load is called a point load. And the second one is a uniformly distributed load. Suppose I am applying some amount of force with using all my hand. Suppose I am applying with my finger, it can be treated as a point load. If I am applying with the full hand, suppose I am applying with my full hand, it can be treated as a uniformly distributed load. So uniformly distributed load can be considered or can be represented as a force over a length or force over a area. Okay. Here is a graphical or schematic representation of point load and a uniformly distributed load. First one is a point load. Here W1 and W2 are the point load acting on the beam AB, which is supported at the points R, A and B. So we will be representing the point load as a simple arrow, either in the upward direction or in downward direction or in inclined direction or in horizontal direction. So any way we can apply a point load. The next thing we will be dealing with the uniformly distributed load. So uniformly distributed load normally represented by this symbol, a spring over a beam. or in some case we will be using this symbol, equal arrows having equal height. These are two types of representing uniformly distributed load. In point load, the unit will be given in Newton or kilonewton or meganewton. But in uniform distributed load, the unit will be Newton per meter or kilonewton per meter or meganewton per meter. So it will be acting, suppose let it be 5 meter, let the length of the beam is 5 meter and the load is 2 Newton per meter. So total load acting on system can be calculated by multiplying 2 Newton over a length of 5 meter. For 1 meter, we will have 2 Newton. For 2 meter, we will have 4 Newton. For 3 meter, we will have 6 Newton. And for 5 meter, we will have 10 Newton. That is the value of the uniformly distributed load. And normally we will be replacing, for solving problem, we will be replacing this uniformly distributed load with a point load. We will be replacing uniformly distributed load with a point load. And which can be, so here I am replacing the uniformly distributed load with a point load. Let me erase the extra line. Okay. So here is our uniformly distributed. I am replacing with a point load. Again, let it be 2 kilonewton per meter over a length of 5 meter. So the value of the load will be 2 into 5, that will be equal to 10 Newton is the value of the load. And we have 5 meter length. And we will be replacing with a point load of intensity 10 kilonewton. We got this 10 from calculation of 2 kilonewton per meter over a length of 5 meter. So total 10 Newton is the intensity of the force. And it will be acting at the midpoint of the entire length. In this case, the load is for a length of 5 meter. So it will be acting at the midpoint. So it will be acting at a distance of 2.5 meter from the left end. Okay, that's how we will be replacing our uniformly distributed load with the help of a point load. The next thing we will be discussing the uniformly varying load. But normally we will be representing uniformly varying load with the help of a triangle or a arrows having increasing dimension. Here is one example. I will normally by a triangle, arrows having increasing dimension. The intensity of this load is given by area of the section. Here we don't have the full triangle, so we cannot solve this as a uniformly varying load. So we will be dividing it into 2. So I will discuss it later. First of all, this is the example of a uniformly distributed varying load. Initially it is 0. Finally, it got its maximum value. Suppose let it be 2 Newton and it got a length of 2 meter. So again, I want to represent the same force, same system as a point load. So in the previous case, I got the intensity by multiplying 2 kilonewton per meter with the distance 5 meter. So I got the intensity as 10 Newton. Here in this question, it's a uniformly varying load. And it's got a maximum value of 2 Newton at the right end. And it is acting over a length of 2 meter. We will be replacing with a point load whose intensity is given by area of this section. You can see that it's a triangle. So area of the triangle is given by half BH equal to half base equal to 2, height equal to 2. Here base equal to 2 meters, so I have substituted 2, and height equal to 2, again I substituted 2. So its value is 2 got cancelled. 2 Newton is the intensity of this force. 2 Newton is the intensity of this force. So we got the intensity of the force. The next thing will be, we have to find where it will act. It will act at the centroid of the triangle. So here is it is a right angle triangle. Its centroid will be here, and it will be represented by b by 3 from the base. From the altitude, it's a 2b by 3. So we will be representing with a point load having 2 Newton at a distance 2 by 3 from right end, or 2 into 2 by 3 from the left end. This is how we will be replacing a uniformly varying load. So in this figure, they have given a portion of the triangle. So in this figure, we have to consider both uniformly varying and uniformly distributable. So I will be dividing this into 2 portions. The bottom portion can be treated as a uniformly distributed UDL, and the top portion can be treated as a uniformly varying UVL, uniformly varying load, so that we can calculate the total value of the force. So these are the 3 types of loading we are experiencing in our problems. Okay, we'll go to our next slide. And next we are going to discuss what are the types of support beams. The first thing we will be discussing the simply supported beams. Simply supported means, suppose here is one wall is here and another wall is here. I am placing a beam over this. This is called simply supported. Suppose when we apply any force on the top of the beam, the wall will offer some reaction. Suppose we apply any force on the bottom of the beam, the wall will not offer any reaction, the beam will move upward. That is meant by simply supported beam. It will only have the upward reaction, that too in the vertical direction. Suppose I am pushing this beam towards left. What will happen? Anything will restrict, only friction will restrict. And if we neglect the friction, the beam will move in this direction. So there won't be any reaction. The beam will move in the direction of the force applied. So in simply supported beam, the beam will experience only vertically upward reaction. So here is a representation of the simply supported beam. We will be representing the reaction as an upward arrow, and we will be denoting as R. As it is acting on the point A, we will be denoting as RA. So if we do a problem, you will get more idea about that. And before that, we will be going through another types of support, roller support. Roller support is almost similar to simply supported beam. The only difference is we have a beam, and here is again I am drawing the same wall here, and I have placed the beam over the wall, and in additional I have placed the 2 wheels on the under the beam. So again I am applying the upward load. What will happen? The beam will offer a downward for the downward load, the wall will offer a upward reaction. Suppose I have applied a horizontal load, so it will freely move through the wall. Suppose apply upward load, what will happen? The beam will move upward. So roller support is almost similar to simply supported beam. So the only difference is, in simply supported beam, if we apply any horizontal load, the beam will move forward if we neglect the friction. If we consider the friction, the beam will have a reaction in the. Okay, so we will go through one problem so that we will get an idea about how the simply supported beam act and how to calculate the reaction. So here is our problem. So we got three loads, 3 Newton, 4 Newton and 5 Newton, acting at a distance 2 meter from point A, 3 meter from point A and 5 meter from point A. So to solve this kind of problem, we will have to assume that, or the condition is the system is to be in equilibrium. For the system is to be in equilibrium, it has to satisfy two conditions. The first condition is net force acting on the system should be 0, and net moment acting on the support at the end point should be 0. By satisfying these two conditions, we can solve this kind of problem. So we will be applying the first condition. The net force on the system is 0. The first condition is net force on the system is 0. So we will be calculating the force. First one, 3 kilonewton downward direction, 4 kilonewton downward direction, 5 kilonewton downward direction. So we got three forces, 3 plus 4 plus 5. That's equal to upward force. Here is a reaction at a point A. We will be naming it as RA, and here we got another reaction. We will be naming it as RB. Okay. So these two will be acting in the upward direction. So we will be writing this is equal to RA plus RB. Okay. And the next we will be applying the second condition. At the end point, moment equal to 0. Or if we are considering any point in between, suppose any point in between, total moment on the system should be equal to 0. That is, total moment in the clockwise direction and a total moment in the anti-clockwise direction should be 0. Okay. So we will be calculating the moment with respect to point A. Moment is obtained by force into distance. First, we will consider the 3 kilonewton force with respect to point A. When we apply this force, it will try to rotate the system in this direction. So it will create a clockwise moment, and its value is given by force in distance, that's equal to 3 into 2. And the second thing, the 4 kilonewton forces, its effect also, it will create a clockwise moment, and its value is given by 4 into distance from the point A, is equal to 4 into 3. The third force, 5 kilonewton force, it also create a clockwise moment. Its value is given by 5 into 5. This is the total clockwise moment on this system. And we have one more force at the NP. It is acting in the upward direction. So it will create a anti-clockwise moment. And its value is given by RP into distance. That's equal to 5. So there is some confusion is there. Actually the total distance is 5, so let it be 1. Let it be 1. So we can write this as 5 into 4. Okay. So we will be getting the clockwise moment and the anti-clockwise moment. So we will be getting 3 into 2 plus 4 into 3 plus 5 into 4. These are all clockwise moments, and that's equal to anti-clockwise moment, RB into 5. So the only unknown is RB. By solving this, we get the value of RB as 7.6 kilonewton. So if we got the value of RB, we can get the value of RA from the first equation. We have already formed one equation. That force is equal to 3 plus 4 plus 5 minus RB will give us the value of RA. So this is how we solve and find the reaction of a simply supported beam. Here we are discussing only point load. So in the next question we will be discussing uniformly distributed load. So in this question we got a uniformly distributed load. So the first of all I will be replacing this uniform distributed load with a point load. So I will be drawing the figure once again. So okay, so I will be drawing the figure once again. Here we got a reaction, and here we got a force, and here another force, and here one reaction, and we got a uniform distributed load over a length. So we will be replacing this uniform distributed load with a point load. So it will be acting at the midpoint. The total distance is 1.5 meter. So it will be acting at the midpoint. It will be 0.75 distance, 0.75 at a distance 0.75 from here and 0.75 from here. And its value is given by 2 kilonewton per meter over a length of 1.5 meter. So its value is equal to 2 into 1.5. So here we have 4, here we have 1.5. So here 1.5, here 1.5, and here 1.5. And we will be writing this reaction at point A RA, reaction at point B RB. The first thing we will be writing RA plus RB is equal to total downward force. So RA plus RB is equal to 4 plus 2 into 1.5, 3 plus 1.5. So 7, 8.5. And the next thing we will be applying the moment at point A. So net clockwise moment is equal to net anti-clockwise moment. Again, the moment with respect to point A, first force 4 kilonewton per 4 kilonewton. It will be creating a clockwise moment. Second one 2 into 1.5. Again, it will be creating a clockwise moment. Third one 1.5. It will be creating a clockwise moment. The last one RB, it will be creating a anti-clockwise moment. And the moment, the value of the moment is given by force and distance. First one equal to 4 into 1.5. Second one 3 into 1.5 plus 0.75, 2.25. And the third one 1.5 into 3 plus 1.5, 4.5. And the fourth one RB into 6. So getting total clockwise moment and total anti-clockwise moment, we will be, this is the total clockwise moment and this is the total anti-clockwise moment, RB into 6. Getting these two, we will be getting the value of RB as 3.25 kilonewton, and by getting upward and downward force, first one 4, second one 2 into 1.5 and third one 1.5 minus the value of RB will give us the value of RA. So we got the value of RA and RB. This is an example of uniformly distributed load. The next thing, we have a uniformly varying load. This is the same question we have taken as an example while we studying the uniformly varying load. So we cannot directly apply the uniformly varying load equation in this question. So we will be dividing it into two portions. The first portion is this is first portion, this is second portion. So first portion can be treated as a uniformly varying load, and the second portion uniformly distributed load. So if we replace it with a beam, got a beam here with the support reaction at two ends. First of all, we will be replacing the second force, that is a uniformly distributed load. Its value is 2 kilonewton per meter over a length of 4.5 meter. So it will be acting at the midpoint, and it is value is given by 1 into 4.5. This is the second force. Okay. The first force, the value is given by area of the triangle half BH, where base equal to 4.5 and a height equal to, we will be analyzing this much portion only. The total height is 2 kilonewton and up to this it is 1 kilonewton. So we will be analyzing only 1 kilonewton only. So height is equal to 1. So its value will be 2.25 kilonewton is the intensity of this load. And it will be acting at a distance h by 3 from the base, or b by 3 from the right angle side, and 2b by 3 from the zero acute angle side. So the total distance is 4.5. So it will be acting at a distance 3 meter from here, that is 4.5 into 2 divided by 3, and it will be acting at a distance 1.5 meter from here, and its value is 2.25 kilonewton. So we will calculating the total clockwise moment with respect to point A. So first one, this will create a clockwise moment which is given by 1 into 4.5 into 2.25. 1 into 4.5 and 2.25. Again 2.25, this will also create a clockwise moment given by 2.25 into 3. And the remaining, this is the total clockwise moment. Then the total anti-clockwise moment due to RB, it will create a anti-clockwise moment which is given by 4.5 into RB. And we will be equating these two, we will be obtaining the value of RB as a 3.75 kilonewton. And from that, from equating total upward force equal to total downward force, we will be obtaining the value of Ri as 3 kilonewton. Okay. So these are the questions from a simply supported beam. So this is a question of combining uniformly distributed load, uniformly varying load, and a point load. The first thing will be replacing the uniformly distributed load with a point load. So it will be acting at the midpoint. Its value is given by 2 into distance. Its distance is 1. So again it will be 2 kilonewton. Next thing, uniformly varying load. It will be acting in distance of hb by 3 from the base. So base equal to 3, it will be acting in distance 1 meter from here and 2 meter from here. And its value, we will be replacing it as a point load. Its value is given by half BH. Half base equal to 3, height is equal to 2. So 2 got cancelled. Its value is equal to 3 kilonewton. Okay. And we will be applying the moment, clockwise moment. 4 kilonewton create a clockwise moment which is equal to 4 into 1. Again the 4 will create a clockwise moment 4 into 2. 2 kilonewton will create a clockwise moment is equal to 2 into 1.5. And this 3 kilonewton will create a clockwise moment which is equal to 3 plus 2. 3 into 5. And RB will create a anti-clockwise moment equal to RB into 6. So getting these two, this is the total clockwise moment and this is the total anti-clockwise moment. So we'll be equating these two, we'll be obtaining the value of RB, and equating upward and downward force, we'll be obtaining the value of Ri. Okay. The next thing will be an overhanging beam. So we'll be discussing that in the next class. Okay. Thank you.